Alright, evening everybody. Are we all ready? Turn that off, put that on silent. Just do some fiddling. We've got it down to 29 concurrent viewers. Excellent. I think we're running on a slightly low bandwidth at the moment, unfortunately. Don't know why. Let me check. Everything's hooked up properly. Okay. Doesn't sound like the sound is going crazy. Right. Give it a couple of minutes for some people to turn up, and then we'll talk about tea. So I might do a brief tea tutorial. Key with tea is to keep it simple. You don't, there's lots of silly things you can do with tea, but you don't really need to. Alright, it looks like we're heading towards our standard numbers, so let's get started. Alright, so today, what's everyone gone for in the tea? Coffee? No. So it'll never be coffee. I do not drink coffee. Refresh the page. Whiskey. Why would you drink whiskey? You could have tea. Okay, so what have we got? Yeah, no, definitely not coffee. Russian Caravan, Sydney Breakfast, Chocolate Toe Oolong, Chalky Milk. I do like chocolate milk, but it doesn't agree with me. Tiguan Yin, third week of Tiguan Yin, Silver Moon. So, what I'm actually drinking this week, not the last lecture, mind you, so to those who are asking, there will be a lecture next week. We'll do a bit of a cap to the subject. But this week, let's get the angle right here. Hang on. Where's OBS? See if I can do this without making the webcam fall off the thing. A little higher. Alright. Thus begins the tea tutorial. What we have here is my single favourite tea in the whole world. Nothing fancy. Classic Earl Grey. I don't know if it shows up in the light particularly well. Need better lighting in here. Get ready to get nauseous. So I swing this around. See if I can get the light on the... Crazy. There we go. Proper Earl Grey. Fairly cut up leaves. In person you can see the kind of almost bluish hint of the bergamot oil. So, the way I make tea, usually, this is, just the classic I want a cup of tea making tea. So I do have a teapot. So if I want to make matcha, things go a bit different. But, mug about yay big, standard mug. Standard tea strainer. Full size one though, not the little balls. I don't like them. They tend to leak tea everywhere. Mind you, I've already leaked tea in there anyway. Get a consistent dosing spoon. So it doesn't have to be like a specially made one, but always use the same spoon when you're ladling out tea, because then you know what it is relative to other ones. Per cup, one level, it should be about a teaspoon. Almost every tea is about a teaspoon for a single cup. It's only things like oolongs and stuff like that, or white teas, where you might want to vary that. This is quite a strong black tea, so I also add sugar to it, 1 teaspoon. Little pro tip, put it in the basket with the tea, because then it dissolves really easily as you put the water in. So for black teas, you want very hot water, almost boiling. For most cheap black teas, it's not going to make a difference if it's boiling water or 90 degrees or so. Right. There's lots of fine details about the precise brewing temperature for different teas. Most of it is almost completely unnecessary. Most things you can get away with water that has just been boiled and left to sit there for just a little bit. So it's still steaming, but not necessarily right on the boil. If you start fiddling around with pu'er and stuff like that, you may want to get a kettle that will boil it to exact temperatures, but not important. But here, hot water. Straight in. And then, don't just let it sit there, move it around a bit. It is interesting to watch it if you let it sit there for a bit, because you'll see the tea infuse very, 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 very slowly. But the tea with, or the water with the tea in it, well, it's not really a different density, but you can see the convection currents in the water, and you want to sort of speed things up, because if you rely on the convection currents, you'll especially with black teas, you'll get a very, very bitter brew as you wait for it. You want to speed it up a little. And there's 2 ways you can speed up chemical reactions, or almost every chemical reaction. You can heat them up. You can't do that because your water is already essentially at boiling point with tea, or move things around. That is from having a chemistry degree as well. That's not just made up. So move it around a bit. And then the rest is kind of up to you how dark you want it. So you need to learn what colours your tea goes to. So most green teas stay fairly light. Black teas will get fairly dark, of course. Or in the Chinese tradition, red teas, because it gives you a red brew. But you have to learn personally where you want to stop. I don't like them too bitter, so I tend to stop earlier than some other people. Things especially like Earl Grey, anything where it's got the leaves chopped up very small, be very cautious about leaving it in for more than even a minute. Green teas you can usually leave a significant amount longer because you have whole or close to whole leaves, and they infuse a lot slower. A lot of green teas, in fact, you can reuse the same leaves. Black teas generally do not do that. So you can see Earl Grey's fairly chopped up, so you don't need to put it in for very long, and you definitely can't reuse these leaves. If you get a nice Darjeeling, technically a black tea, maybe reuse the leaves. And there you have it. One nice, hot, warm, slightly sweet cup of tea. Some general things. I very strongly disagree with putting milk in tea. I think it ruins the flavour. Never ever put it in Earl Grey. The citrus in Earl Grey will just completely mess with the milk. Never put milk in green tea. That's also completely insane. But if you really have to, English breakfast will survive milk. English breakfast, Irish breakfast, those sort of strong black teas. Green teas and honey are okay, but usually green tea is fine by itself. But like I said, milk doesn't particularly agree with me all that much, so I won't put it in. It also does overwhelm the flavour very, very, very quickly. Tea bags, oh, no, not tea bags. Tea bags are fine. There's nothing particularly wrong with tea bags. You just got to get good ones that don't give you the flavour of the tea bag instead of the tea. That's the real problem with tea bags. So if you get ones that are made out of silk, they're really nice because you just get the flavour of the tea. That's true. Traditional Indian chaya does rely on being milk. So if you're going in that direction, that's a bit different. You're talking about sort of specific teas. Thai milk teas and stuff, of course, are different. But a good masala chai, that's you've got the spices there, which are kind of stronger against the milk. Oh yeah. So there's obviously wild disagreement about whether you should do this or not. Tea is a very personal thing. This is mine. Do what you like, really. Okay. So that's the special stream extra. Get to see me make tea. When I get a better webcam, maybe I'll do one that I can bring with me. I'll do matcha, but that won't happen for a while. Okay, so let's begin. Why is there a picture of me on the screen? Okay, so let's start the recording and start the lecture properly. Alright, so welcome everybody to week 11 of Programming Fundamentals for autumn 2021. We are very, very rapidly approaching the end of the subject, and this will be sort of the last lecture with content that you can make use of in the subject, essentially. So the lecture next week is basically going to be when everything's due. So there's like literally no time to teach you anything new. Sorry, I think my bandwidth is a bit choked, so everything's loading a bit slowly at the moment for some reason. Hopefully the stream's doing okay. Let me just kill that. Try that again. So this week, as I mentioned last week, is essentially a requests episode. So when I get Ed loaded, we'll find out what everyone voted for. I think I already know, but we'll try and go over some of the things that everyone's waiting for. And hopefully I'll also get to those questions by the end of the night. So, what topics did we end up with in the view? So, there we go. We've had a bit of a tea review. So if you didn't see that, you're watching the recording. Sorry, you'll have to go and watch the stream to get the special tea extra bonus content. The people who hear live. Oh, technically it's recorded anyway, but so, what have we got? Some pretty high votes for array list and linked list. An office well, there you go. Tutorial on how to make a cup of tea. An office tour. Well, I can do that. That's very, very quick though. Breaking and continuing loops. And what's a switch statement? Breaking and continuing. Yes. So, let's look what else. Interfaces. How to do part of the assignment. Linked lists from Nick, but it's got some votes. Linked lists. The bounce down. I haven't quite set that up yet. I have a feeling that this might be Nick. That is to say, I know it's Nick. Linked lists. Okay, so linked lists and array lists are sort of our biggest ones, so we'll go with that first. And then see how we go for time. But clearly obviously it's linked to the assignment, so it's pretty useful to talk about. Those who haven't noticed as well, just in case you didn't spot it, because pointing no fingers, undergraduates are terrible at reading instructions in general. That's not to say only undergraduates are. Almost everyone is terrible at reading instructions. But in the instructions section for the assignment, there are two separate videos of me talking about linked lists. That includes some pretty leading information about how to do some of the tasks. So one is just a relatively quick overview. The other one is actually the lecture I gave in Programming 1 last year. Programming 1 this year, about basically the same topic. So you do already have some extra material on those linked lists anyway. And everyone wants to talk about week 9. Week 9. So what's in week? Oh yeah. I can see who's. I believe I've said that several times. That's why you can post anonymously, and the staff can still go look at your code. We know who you are. I mean, you've all been very good, but that also helps stop abuse. So do have a bit of buffering here. Annoyingly. Apparently got an excellent connection. Now, let's hope that's going on all right. Let's talk about linked lists. So I'll try and talk a bit about array lists as well, but let's talk about linked lists. Yeah, it seems to be a bit laggy. I don't know why. I think I need to get a more complicated streaming setup where I've got one thing sort of controlling the streaming and the other one doing the work, but the uni doesn't pay for that. Yeah. Okay, so based on some of the feedback we're getting in the chat, it looks like the internet at uni is a bit flaky at the moment. So if we do lose something here, I am recording it. Yeah, use my streaming revenue for a better setup. I wish. I am recording it, so the if the stream recording turns out to be terrible, I'll upload the other recording as well. And the other recording is local, so it's getting the whole thing. So I'm also on the wired network as well, so it should be separate from the any Wi-Fi problems the university's having, but it's not separate from any internet problems the university's having, which may involve people digging holes in the internet, which has happened before. So the way the campus is hooked up, the main internet... The main internet connection comes into the basement of building 1, I think, and then there are various branches that go out to the different buildings, but there's kind of circuits, so you can get to building 11 via the direct connection to building 1, but there is also a connection over to building 4 that goes back to building 1. And once upon a time, when they were knocking down the old building 2 that none of you will know, they dug straight through the connection between building 11 and building 1. And then everyone's internet was still working because it was rerouting through building 4, but it was just agonizingly slow. But it took a while to show up because everything was still kind of working. So never underestimate the power of a guy with a shovel. Okay, on to linked lists. So, as we've said before, so what I might try and do is I'll talk a little bit in general about linked lists, and then maybe try and give you, without giving you actual code, something close to a step-by-step of how to do some of the operations. So lists in general are ordered, linear, and contiguous. So this means basically if it's ordered, we can say one element is before another consistently. It's linear, so there's no branching in the ordering. And it is contiguous. I've got a better way of writing that. It's contiguous in the sense that there are no gaps. Why am I doing that? I can just undo it. Much faster erase. So if we've got a data structure that is ordered, linear, and contiguous, what this means that we forget how to spell. So I am simplifying a little here, so there are technically other ways we could do this. But if we've got an ordered, linear, contiguous data structure, then we can use an index to access it. So we can use a number and get the element at that number. And the indices go from 0 to size minus 1. Obviously, there are other indexing schemes, so there are technically languages out there that you go from 1 to size, but I include this in particular here right now. There's a few people who I've helped out so far, or pointed some things out, who've forgotten that these things are indexed from 0. Right? So when you're having some funny problems with your add method or your add at, remember that 0 is the number of the first index, not 1. And it goes to size minus 1, not size. Hint, hint, hint. So there's one other thing we can add to this that distinguishes them from arrays. Sorry. Let's do it this way. Arrays plus lists. And that's the ability to add and remove elements. So arrays are almost lists. And in a sense, a list is a way to get behavior that we expect from an array, but also the ability to add and remove elements. And if you sort of think about that a bit, that kind of gives you a lot of structure on how a list should work. So as long as you're not modifying it, externally it should look exactly like an array. It may be faster or slower or something. Like it may not, internally it'll work differently, but from the outside it should look pretty much exactly like an array, and that's what you're aiming for. A list is basically an array that you can grow or shrink. So we have, amongst the options, a number of ways that we can make lists. So these are not the only ones. There are other ways of doing it. Depending on the time, I can show you a really, really nice functional way that will confuse the hell out of you. So one way that we can make a list is just use arrays as the backing data structure and hide the resizing. So in Java, that's what ArrayList does. And the stuff in the Week 9 lab. Or we can use pointers / references. And this is how we get a linked list. Which is, of course, as you know, your assignment. So by the end of the subject, will hopefully have built a simple version of 2 of the major Java basic data structures. And knowing how they work is really useful, because later on that will help you make sense of why one is useful for certain tasks and the other isn't, and vice versa. So to some extent, this one is simple, in that it's just using an array mostly. So with an array list, as long as the size of the list fits in the array that you're using to actually store the data, it's easy. You just stick the next element on the end. If you want to get something, you just go to that point in the array. That's all well and good. So as long as you've got an inbounds request, it's inbounds in the array as well, so getting it out is super easy. It's easy to, like, if you want to replace an element at a certain index in the list, again, it's super easy. It's just overriding an element in an array. So when the array fills up, we create a new bigger array. Came out weird. We move the data over to the new one. And then replace the old with the new. So in Java, because Java has garbage collection, and only has references and doesn't have pointers, this is actually all fairly simple and handles all the memory allocation. But again, of course, I'm simplifying things here. There are details in this to make it work. But once you get that, okay, once the array's full, I need to create a bigger array, copy everything over, and then replace the old one with the new one. Everything else is actually pretty simple. You can just kind of use it like an array. The only extra thing you need to do is keep track of the size of the list as well. So you need to do something extra to keep track of how big your list is, as compared to how big the array is, because the array might be this big and you're only using this much to store the list in it. And then when the list size reaches the array size, that's when the array is full and you have to create a new one. So keeping track of the size of the list is an integral part of building an array list. If you want to build a fully functional and useful one of these, of course there are other considerations like what's the optimum size for the array, how do I do the resizing schedule, what other sort of tricks and interesting things can I do to make it fast and easy to work with. But in a sense, if you want to implement a list using an array, this is the absolute basic bones of it. This is what you need to do. And that's, if you think about this carefully, this is the answer to the Week 9 lab. Oh, it's my face again. Yeah, so there's that text again. So that's kind of it with an array list. If you have, on the outside it looks like a list, on the inside it's an array plus probably a variable to keep track of the size, and when you fill up the array you make a bigger one, move everything over and copy the new one over the old. A linked list, however, uses a completely different structure. So externally, a linked list still implements a list. So it still has those behaviors that you expect from a list. It should be an ordered, linear, contiguous data structure which you can add and remove elements from. So just to be clear about that, you can't add and remove elements from an array. Once you create an array of a certain size, it always has that many elements. You may not be using all of them, but they're always there. You've allocated that much memory. With an array list and a linked list, the amount of memory allocated to store the list is somewhere approximately the same as the size of the list itself. Right, up to a little bit of error in an array list and some overhead in a linked list and stuff like that. But, what color is my pen? So the way a linked list works so it uses some sort of node structure to store the data and a pointer to the next node. So a linked list is built out of these small building blocks which you put together to form a chain of nodes, and I guess that's it. That is the list structure. Right? So externally, when you write the wrapper class around it, it looks the same as the array list, because you still say, you know, I want to add this element. It'll find the place at the end to put it, stick it on the end. If I want to get an element at position 3, it goes to the third node along, well, the fourth node along, I guess, and gets that element. So externally, it doesn't care, but internally, the way it's sitting in memory is completely different. So our linked list then looks like something like this. Ooh, oops. it's very hard to draw a straight line on this thing. That is to say, I'm terrible at drawing straight lines. It's got nothing to do with the tablet at all. It's me. So we've kind of got this box. So if you remember back to our object-oriented design thing, we abstract the internals away. We encapsulate the data. So we've got this thing that on the outside we call a linked list. But on the inside of it, we've got usually a variable that says where the head is. So the head is the first element. So the head of the list. And then we've got a node. So this is a node. And it stores a data element. Whatever. And then it says where the next node is. So this node class is the thing that you build in the first part of the linked list thing. So part B, section B, part 1. I've forgotten how I labeled things. And the node by itself, all it does is just have the data and the pointer to the next thing. To make the linked list out of them, we need to add basically apart from all the methods that make it work, we need to add two things. We need a head variable that keeps track of where things are. And typically, so it's not the only way to do it, but normally we terminate the list with null, so we know when it's finished. So we don't have a special node that says this is the end or anything like that, because that can get confusing for various reasons. We have this special value in Java. If you're doing it in Python, it's called none. C++, it's a null pointer. In C#, I think it's null with a capital N. So pretty much every language has some idea of this thing, the empty value. And once you get to that, you've run out of nodes in the list. So then, where do we get like our indices? So remember we said a list is kind of like an array, except we can add and remove elements. Where do we get our indices? So in an array list, it's easy to see because the index of the element is just the index in the backing array. Unless you're being fancy with your arrays and then you've got to do some calculations. Where do we get our indices in a linked list? Well, it's just how many steps along the chain we have to go. Right? So the head node, so the thing that the head variable is directly pointing at, is element 0. If I have to go one step from there, it's index 1. If I have to go 2 steps from there, it's index 2. So again, indices start from 0. This has size 3, so I have 3 nodes, one after another, in this exact order. I have the 0 node first. It doesn't have to store this information. It has to store the size somewhere, I guess. Well, if you want, you can recalculate the size every time. But it doesn't have to store the index. But the head is the 0 node. The one after it is the 1 index node. The one after that is the 2 index node, and so on and so forth. So if we want to add something to a linked list, how do we do it? So in an array list, it's fairly simple, because in an array list, if you've got an array and you've got the size of the list, then the next available space in the array is the element indexed by size. So you put it there and you increment your size variable. So if you're paying attention, that's a big hint for week 9. With a linked list, you've actually got to iterate along the list. So you've got to start at the beginning and move one step along. Those of you who are thinking or being a bit more cunning, you can make this a bit simpler. So if you keep track of where the end of the list is, you can make it easy to add things. But that adds an extra complication. You've got to keep track of more information and do things. So it's kind of a trade-off, like almost everything in programming. So if I've got my linked list, it looks like this. So the head points to element, this is element 0, that points to element 1, that points to element 2. Again, they get those indices implicitly just by being in that order. Like there's no other way to arrange the indices. They're defined by their link in the linked list, or their position in the list. If I want to add, so let's put some numbers in here, 3, 5, 2. If I want to add 7, what do I do? So I start at head, or the thing that head is pointing at. And then as long as my next is not null, we move along one step. So is the next of 3 null? No, it's the element that contains 5. So we move to here. Is the next of 5 null? So this is not equal to null. This one's not equal to null. Now the next of 2 is null. So we've found our position that we want to add the new node. So let me this is the problem of getting rid of all the tools to give me greater space. I no longer have all the toolbox there. So in step B, or phase B of adding it, create a new node, 0.2. So I'm using 2 as a shorthand here. Add it. And then point the new node at null. So what I'm doing is creating the new node, which happen to have value 7. Taking what 2 is pointing at and pointing it here, and then pointing 7 at null. So if you go through the steps in that order, then things are okay. So where this goes wrong is if you forget to, you point 7 at null and forget to point 2 at 7. Right? Or you do your count wrong and you point 7 at 2 and 2 is pointing at null, but then 2 is not pointing to anything, or you point 5 at 7 and 7 at 2 and you're just off by 1. Okay. Or you try and point null at something and then that'll just fall over completely. So, like, that's sort of all there is to adding it. It's start at the beginning, go along the list until you find the last element, so not the null, the one just before it. Create your new node, point that last element at the new node, and point the new element at null. And that's it. If you're keeping a size variable, you have to increment the size variable, of course. Don't forget to do that. If you're not keeping a size variable, then you don't. I strongly recommend keeping a size variable, like recalculating it every time as its own potential places to add error. So we have a special case which is an empty list. It also works for when you're adding at position 0. So there's another method you have to work on where it's added at position. What we do in this case is create a new node, point the new node at the head, even if head is null. And then set the head to the new node. Again, this is one of those things where the individual steps are fine, but it's the ordering that's really important. So if you get the ordering wrong in these, things go funny. Right? So if you set your head to the new node, so you create the new node, set the head to the new node, then you've lost the old head and you can't point the new node at it. So if the head was null, then you get away with it. But if you're trying to add an element to the very start of the list, then you've just dropped the rest of the list. So what we have is something like this, Then we create our new node, point it at the old head. So this is 1, 2, 3, 2, and do that. So then that gives us this. Similarly, if we have the head pointing to anything and we want to add something at the start, then we can create our new node, point it at the old head, and then point the head. So 1, 2, 3. Point the head at the new one, and then it works exactly the same. Oh, I need a context sensitive image of myself. And I also need to make more tea. So if you think carefully, however, what I've described in the add and the special case there actually covers the add and the add-at method completely. The only difference with add and add-at is instead of, so add-at is where you're given the position. I'm just using at to make it a bit clearer. The only difference between that and add is that instead of just going all the way to the end of the list, you just count. So if you want to add it at position 3, you count up to position 2 because you want to add it after that point, and position 2 is the last spot where you've got the link to the node that comes after the new one and the node that comes before it itself. That's your current one. So just to please everyone, second cup for the evening is going to be Sydney breakfast. Also a black tea, it's kind of like, I think I said before, it's a mild Earl Grey. I recommend it with sugar, but it is mild enough that you can drink it without it if you don't steep it too long. So if you only let Sydney breakfast sit for like a minute or so, you can quite happily drink it without sugar. Unlike Earl Grey, which will already be too strong at that point, in my opinion. I also used too much water in the Earl Grey, so it's only going to be half a cup. You shouldn't be buying me tea. I don't need to do that. I've got a pile there. I just bought some Earl Grey anyway, so that's fine. Yeah, side diversion. We've got a claim that sugar kills the flavour of tea. It can. Actually, as the following comment says, it depends on what the tea is. So something like Earl Grey is a very, very strong tea, or something like English breakfast. And they're robust enough to stand up to sugar. If you put it in like a white tea, that's just going to completely wreck it. Um, like yeah, if you're drinking white tea, you should be thinking very carefully about how you're making it and how you're steeping it and stuff like that. But strong black teas, sugar or milk is usually fine. Just happens with Earl Grey. I think the milk ruins the citrus flavor, but that's a coincidence. Most green teas you can make definitely. Well, as said, some people do put milk with them. Green teas cover a lot of ground as well, so it's a bit hard to. It's not really one size fits all. Um, some of them I will just have straight. Some I'll put a little bit of sugar with. Um, yeah, so personal preference. Okay. So let's not jump to there. Let's see there. So let's add, what are we doing for time? Okay, we've got about 25 minutes left. So let's do getting something from a linked list. So get 3. So we'll assume the list is big enough. Obviously with all of these you have to put bounds checks. Because if someone tries to get something that's -5, then you just say you're an idiot, stop doing that. If they try and get something off the end of the list, it should refuse to do that as well. So typically the way to refuse to do that is to actually crash. So if you're doing it in well, depending on which version, if you're doing something like this in C or C++, you'll probably get a seg fault. Or you might just random junk out of memory. If you do it in Java, you'll get a out of bounds exception. In ours, we're handling it a bit simpler. We're just doing nothing. We're returning a default value. Read the description exactly for what the default is. So, to get something out of a list, assuming the thing is in bounds. Apparently I just can't spell head. So to do this, we need probably a while loop. And we start off with at position. At pos 0, which is here. So we also need something like a current node. So this one is actually kind of implicit. Actually, let me make that. A dash line. And then no, it's getting too close to actually just giving you code. So then while pos is not equal to this value, we move current along one step. So to retrieve something from a list, we basically need two things to keep track of where we're up to. So we need what our current position is to compare it to the required one. So just keeping track of how many steps we've taken. So a position or a count or something like that, or number of steps. And we need a variable that's going to point to our current node. And while the position is not at, or the current number of steps, or however you want to think of it, is not what we want, we move that up one using the getNext method on the node. Right. And then return that value. So again, just stepping back for a moment, from anyone using the list, all they see is they say get 3 and you get a value back. Right. And that's it. What's happening inside of it is the actual thing that makes it a linked list. It's made out of these nodes and you have to iterate along it. So, given that I want to talk about a couple of other things, what I've actually shown you is actually enough to complete the assignment. Right? So there's a couple of little tweaks you have to do for some of the methods, but there's basically only 3 things you can really do with a linked list. Right? So it's the 3 things you can do is start at the head and step along the list until you get to the position you want, and move a link. I guess it's only 2 things really. Not much more than that. So when you're at the position that you want, you can then move the next link to something else. And that's about it. And so when you think of it in terms of only kind of having those 2 operations, then if you can build all the rest of the more complicated things out of that, you're kind of done. Everything else is just iterating along the list the right number of steps. So again, remember, starts from 0, goes to size -1. If you want to insert at position 3, only go to position 2. If you want to insert at position 2, only go to position 1, because if you want to insert here, or if you want to insert before this one, this is the link you have to break, that you have to redirect. So once you do your counting right, then that's almost everything. Okay, so let me just check that there's no crazy questions in here. Facecam the whole screen. Oh, I forgot to. Face is blocking the screen, face is blocking the screen. Don't know if this is right, but I think yes. So just to clear up the relationship of list, array list, and linked list. List is what we'd call in Java an interface. So it's a definition of what a list should look like. It's not a class in and of itself. Array list is one implementation of that. So it behaves like a list and uses arrays to achieve that effect. Linked list is a different implementation. It behaves like a list and uses nodes to achieve that effect. All right, so they're both types of list. Yeah. So what Peter says is right. List is a guarantee that array list and linked list offer certain behavior, that you can do certain things with them. It doesn't tell you how they do them. So how they do them changes. People stop bullying Dylan. Can you change the head variable to a different one? Yes. going through. So there's a comment, there's so many special cases in the assignment. There isn't actually that many special cases. There's basically one special case, and that's where the list is empty. And that only turns up sometimes. So if you find yourself writing complicated if statements, you've probably overcomplicated it. Normally you would only have one sort of if and an else. If you've got if else, if else, if else, something's gone. It might still work, but you're breaking it down further than you need to. Null is evil. Yes, I agree. Null is actually kind of evil. It's all right when you use it in the right spot. If you explicitly use it as a pointer, or in Java a reference, then and you're careful about how you use it, that's fine. It's that it gets used for too much and not properly taken care of. There is a better way to handle non-existent values, but it makes the code more complicated. Do we need to reference the last node to null, or is that automatic? So if you use the single value constructor for the node class, it'll automatically be null. If you use the two value one, you need to do it manually. Itchy nose. Alright, questions in the question thread. Are all the additional exercises weighted the same, or do we need to complete all of them to get the 20%? Yes to both, then those are not exclusive conditions. All of the additional exercises are weighted the same, and you need to complete all of them to get full marks. So, that is yes. Okay, so let's go back to the topics and see what we can cover in the last 10 minutes. So we've done T, we've done linked lists, and briefly array lists. Again, if you were paying close attention there, I actually kind of went through the answer to week 9 as well. Again, without casting aspersions against anyone, one of the problems when you're learning to program is overcomplicating things. So most programming problems are probably simpler than the answer you start off with. So if you can step back, think about what you actually need to do, and I really strongly recommend trying to solve it on paper first. Diving straight into the code is a bad way to get a good solution. You may get a solution, but unless you're practiced at what you're doing, it's a bad place to start. But yeah, the solution to the array list ones and the linked list ones, the assignment, when you figure them out, are actually relatively straightforward. Like there's not a lot of code in any of it. It's just taking a moment to sit down and think about what you're talking about. All right, topics. So array list and linked list done. Office tour and tutorial. So we've made a cup of tea. Breaking and continuing loops. Okay. So do I have enough time to do that? I can definitely talk about a switch statement. Let's start with a switch statement. No, I want you and I want my workspace. So we can probably do break and continue here. Thank you, Nick, for setting that up. So in Java, so you're all hopefully fairly comfortable with if-else statements. They're a way of branching or selecting stuff, a way of making decisions. And in an if-else statement, you have a fairly controlled way of selecting stuff. You have if and a condition. If that condition evaluates to true, it runs the block that is associated with the if part. If it's not true, it goes to the else. If there's no else, it just follows on from the end of the if. All is good. A switch statement is an alternative decision structure. So the way a switch statement works is that you give it an expression to switch on, right, which is kind of like the condition in the if, but not identical. Right. You give it a condition to switch on, and then you give it a series of cases. So where it differs from an if statement in that regard, in that specific regard, is that like an if statement condition can be quite complicated and cover a series of situations. A switch statement, if I switch, for example, on this variable I'm going to put in, the only cases I can have are specific values of that expression. So I can't do the case where I is less than 9. Right? I can do the case where I is exactly 9, but I can't do complicated things. So like in Java, in an if statement, I can do if I is less than 9, do this thing. With a switch statement, I can't do something like that. But what I can do is have specific things. So if it's 1, 2, well, let's do some weird ones. I can have, for example, a case for where the value is 1, or a case where the value is 5. I can also have a default case, and I really should. If you're writing a switch statement in Java and you don't have a default, you should have a good reason why you do not have a default. If nothing else, it should be there to catch when someone puts in an incorrect value. And then what happens is when it reaches this switch statement, it looks at the value of the thing that it's switching on. And as Nick has just put in, it can only be a limited number of things, so you can't just switch on anything. It is getting more expansive as versions of Java progress, but they have a limited number of things which are kind of lowercase e enumerable, which is a byte, short, int, string, a char, or an enum. So it looks at that variable, or that expression, I should say. It doesn't just have to be a variable. It can be an expression that produces a variable of that type, a value of that type, and then says, does it match the value given in this case? So if I is equal to 1, it will start at this point in the switch statement and keep going until it hits a break or reaches the end of the switch statement. So that's another key difference to an if statement. So if this had no break here, then if I got a 1 for I, it would run whatever code I put in here, and then it would run whatever code I put in here, and then it hits a break and it stops. Okay, so it keeps going until it hits either the end or a break. So if it doesn't match this value, but it does match this value, it will start at this point and run till it hits either the end or a break, whichever comes first. If it matches none of them, it will jump to the default and run that code until it hits a break or the end. Typically you put the default as the last one, so most of the time you don't need the break statement, but I strongly suggest writing it anyway. It's good practice, because often what happens is you build these up bit by bit, so you don't want the default. You want to be able to adapt the default when you change your mind later, and if you've got the break statement already there, it works nicely. So if I run this now that Nick has very kindly made that work, this is going to ask for a number. So if I put in 7, we get the default case. So remember, it's only going to do something if I put in 1. Well, it's only going to do a non-default thing if I put in 1 or 5. So if I put in 3, it's the default. So that's between 1 and 5, but it doesn't care. It matches exactly on what the cases are. So if I put in 5, I hit case 5. If I put in 1, I hit case 1 and 5, because again, I is 1, so this one triggers. It starts here and keeps going until it hits either a break or the end. And because I removed the break there, it's just going to keep rolling through. So if you've got a very simple if statement, this kind of looks the same. But if you have a more complicated situation, this is quite different. So you can always take a switch statement and convert it to an if statement. But you can't always convert any if statement into a switch statement. So if, for example, you need the switch statement to do one action on an effectively infinite number of values, and the other statement on an effectively infinite number of values, then a switch statement is not going to work. Because you have to write out explicitly every matching case in a switch statement. However, on the other side, if you've got like small blocks of cases where it's like case 1, 3, and 5 do this task, case 2, 8, and 7 do this other task, writing case 1, case 3, case 5, and then the code reads much cleaner than writing if I equals 1 or I equals 3 or I equals 5. And so you're trading a long if condition for, well, what you'd think of as a long if condition for a short number of cases. Okay. Thanks to this cascade, the way the cases cascade. The other advantage that a switch statement gives you is that does it actually warn you when you're using certain things like an enum? It will tell you if there is not a matching case for every possible value. So you guys don't know what an enum is yet, but basically an enum is a finite set of named values. It's a bit more complicated than that in Java, but that's the primary use. So if you leave one of them out, it will say, hey, that one's not there. So you know when you use it in conjunction with certain things, a switch statement gives you certain guarantees that you've covered all possibilities. How are we going for time? If you're writing long blocks in each case, would you recommend creating a nested scope so variables don't bleed into other cases? That's a tricky one. That's if you're writing long blocks for each case to begin with, you're probably at the point where you want to reassess your design. Oh, Nick made an enum. Where's an enum? So just while I was talking about it, here's an example of an enum. So if you're writing long blocks in something like a switch statement, you want to think about how you might reduce that by packaging things out into methods. If you really can't package them out into methods, then like I can't think of one where you wouldn't be able to do it. So there are kind of some cases where you want to use the slightly more verbose structure of an if statement, because it's harder to miss things than it is in a switch statement. So switch statements work really nicely when all the cases are really short. Okay, so here's a simple version of an enum while we're at it. So it's just called calendar, and it has 12 values and exactly 12 values. It can only be one of those 12 things. It can't be anything else. So it's either January, February, March, April, May, June, July, August, September, October, November, or December. They are in all caps because in Java by convention constants are written in all caps, and these are kind of constant values. Another way of thinking of it is enums are classes where you only have a fixed number of instances. You can't create objects of these, they already exist. So where you've got this, so I've got 12 values there, I can make a switch statement where the compiler will warn me if I've missed one of those values. So that's where it's really useful. Okay, we've hit our time there. Just one last word. So the original question was about using breaking and continuing in loops. At this point, as Nick said in the thing, the general advice is don't. It's one of those things where it is a thing that is possible, but unless you know why you're doing it, don't do it. Right? So all programming languages usually allow you to do bad things, because that's the trade-off of being able to do good things. So breaking is generally avoid continuing more than breaking as well. Breaking is where you have a loop where the best condition to use a break in, and this is not necessarily a good one, is where you have a loop where you don't know how long it's going to go, like a while loop, and you want to stop when you reach a certain condition. So it's like, while true, again, that's a terrible construct, if I equals 7, break. So say you're just reading values in from the user, and you want to stop as soon as you find that thing out, because for some reason it means you can't continue with the code in that loop. Then that's sort of the situation where you use a break. But it's a bit more complicated than the stuff that we really want to look at in this subject anyway. So knowing they exist is useful, but you're not, in terms of the subject, not at a point where we really want to deal with them yet. Okay. So if you want to have a longer discussion about that, we can talk about that in the lab or something like that. All right, so we're now well over time, so we'll stop there. Thank you everyone once again for coming out. Well done on getting to this far in the subject. Only 1 week to go. We're nearly done, and then you can worry about your exams for other subjects. I hope you've all... So again, next week there'll definitely be a lecture. I'll do a bit of a wrap-up. There'll be no new content to learn. You're welcome to ask for me to talk about stuff if you like. But like it'll basically just be a wrap-up and a recap of some things. And tea, of course. Yeah, I'll see what I can do about OBS. But again, thanks everyone for coming out. Have fun and enjoy your last week and a bit. So for those who've got a lab this Friday, your full week. For everyone else, you're working on your assignments and stuff. Again, for those who are struggling with any of the things or need help with their assignment, you can come to any of the labs anytime you like. Right? So obviously we'll help on the discussion board, but in person is often a lot more useful. But yeah, don't stop asking us questions. We're all here. It'll all be good. How do we stop a loop without using a brake? Well, it stops when the condition is satisfied. So you stop it the normal way. What about breaking out of methods when checking for bad cases? So returning early from a method is slightly different. So in a method you use return, not break. And that's a whole other kettle of cats. Yeah, so that's kind of the ideal place to use a break if you really have to use them. You're in a loop and there's certain bad cases, then you break out of it. The same as with a method, if there's bad cases, you return early or you throw an exception. So if it's non-critical to the function, you return early. If it's critical to the function, you should throw an exception. Oh yeah. So a break stops the loop suddenly. So if you hit a bad case in a loop, that can be sort of your justification for breaking. All right. We're now well over time. Thank you, Casper Mattresses. Thank you, Raid Shadow Legends. Thank you, T2, for keeping me going through this whole thing. And I have a pile of wet tea on my desk because I made it here instead of in the kitchen. Share, like, subscribe, show your friends. Join the Patreon, all that kind of stuff. How many subscribers did we end up with? Can't see it. Anyway, again, thank you all. I'll talk to you all soon. We've still got a week to go, but we're nearly there. Well done. All right. Talk to you later. Which page am I refreshing? All right. Thank you all. All right. Talk to you all soon. Have a good Friday evening and a good weekend.